Okay, so nice hat. Um, okay, so today's probably our toughest topic of the year. I mean, you'll see. I'll be a little bit out of my depth, but we're going to study something called probabilistically checkable proofs. It was something we alluded to. Did you grow a whole mustache over Thanksgiving break? Oh, did you have? Okay, that makes more sense. That would take me like 5 years. Okay. All right. So today we're going to do probabilistically checkable proofs. Uh, Do we have all the lectures? Okay, forget all this. Uh, Maybe I'll just talk about what we're doing recently because this is supposed to justify some of the labor. So a few weeks ago or a month ago, we started talking about random walks, starting from a stationary distribution, or existence of. We didn't do that. Then we started doing randomized connectivity, but getting some exposure to hitting times and also looking at the graph Laplacian for the first time. Then we started doing the spectral analyses of random walks. So we started paying very close attention to the eigenvalues and trying to get better convergence rates. Uh, the lecture after that, we did Cheeger's inequality, which related that eigenvalue specifically to kind of low conductance cuts, which kind of give you a combinatorial interpretation of eigenvalues, the second eigenvalue. Then we did deterministic connectivity, where I think things went up a notch. Right? Because then we start talking about expander graphs in particular. These are graphs that mix really well, even though they have like constant degree. Which do they exist? Well, you're going to give two different constructions on the homework uh, of an expander graph. So they do exist, and they have this amazing property where again they sort of behave for all intents and purposes like a complete graph, but they're small, they're sparse, they're constant degree. So for example, in this connectivity, we wanted to take a graph and implicitly turn it into an expander. And we had this trick where, you want to do a random walk on a graph with high degree, and it gets higher and higher because you keep powering the graph to make it mix faster. But of course, a high degree requires many random bits to choose each neighbor. But instead, you create an expander that's sort of smaller, where the number of vertices matches the degree in your graph. But the expander itself has very small degree, like constant degree. So a random step only takes like 4 bits. And you're kind of thinking of the expander as some kind of like pseudo-random dice. So you take a step in expander, that tells you your vertex 100 or something. And you take the 100th neighbor in your original graph and you step there. So you use this expander as like a pseudo-random number generator so that you can sort of simulate doing a random walk in a high degree graph as if it were a low degree graph. Okay. So that was very nice. Um, After that, expanders came up again uh, for sort of more efficient amplification. So instead of like repeating a random experiment, a bunch of times and getting completely fresh bets each time, we'll instead do some kind of expander trick where we think of each node in an expander as a random bit string now get fit into your algorithm. And then you pick the first vertex uniformly at random. And otherwise, you kind of walk around the expander. Each step gives you another random seed to feed into your algorithm. And that'll behave basically no different uh, than just kind of more direct amplification. Okay. All right. So we did amplification last time. Uh, and also expander stuff. So a lot of these techniques are going to come into play today. We discussed something called probabilistically checkable proofs. And well, first, we won't finish the whole thing today. It's going to span 2 lectures. But two, we're not really going to be able to do all the technical details. There's one part I'm going to black box because it requires a bit of Fourier analysis to do, which I have taught in years past. And what I learned is that nobody wants to watch me take the Fourier transform for a whole week. Because all the proofs are like, you take the Fourier transform, you do this, you take it back, and it's done, right? And there's no pictures of graphs or anything. So I learned, well, just black box this one part. So we won't see quite the whole picture, but we're maybe a week away if you did a straight line towards this particular result. Uh, but and at some level, uh, I think the proof is sufficiently complex that even if I had put all the details perfectly on the slides, and as you know, half of the calculations will be typos. Yeah, I think it's just too much to kind of fit in the brain all at once to walk out completely satisfied. But I hope you'll see like a lot of interesting parts because I think the conclusion is dramatic and you'll see the ingredients going in, and that at least suggests there's a kind of some very interesting connections here. Yeah. So I hope it still makes an impression, even if it's not you know, the most suitable for a typical lecture. All right, so okay, I think hopefully you all know these definitions. So a language L is we say polynomial time if there's some polynomial time algorithm. We say if it's non-deterministic polynomial time, which is a ridiculous name. NP if there's a verifier. Okay, so this is some algorithm that takes the input that you want to know if it's in the language. Does it have some independent set of size k? And another bit string that we call the proof. Okay, and the proof should be polynomial size, and a verifier should be able to read the proof. Okay, and I have the following guarantee: if x is in the language, then there should be some proof that makes a verifier answer yes. Yeah, does this have a Hamiltonian path? The proof would be a Hamiltonian path. The verifier just has to check it. Okay, and if x is not in the language, then no matter what this proof is, you should be able to say no. Okay, there's no Hamiltonian path. There's no way you can trick me into thinking yes. Okay, so these are like search questions. Verifiers are sort of like saying when you find a solution, you can recognize it. Okay, so you can recognize a Hamiltonian path, even though it's very hard, apparently, to find one. Okay, of course, it's a very deep question. Why is it so much harder to find it than it is to recognize it? Yeah, somehow we don't have a fully satisfying solution. Okay, now here's a definition that should be new to you. PCP-RQ. So PCP will stand for probabilistically checkable proof. Okay, so as opposed to a proof where you can look at the whole thing, this is some kind of probabilistic relaxation of the notion of NP. Okay? So uh, it's okay. Is for the number of random bits, and Q is the number of queries. So there will be a proof of some polynomial length. Actually, I'm not sure if the length totally matters. I think it's got to be polynomial. But we're going to assume that it's sort of presented in some kind of like oracle model where you can say, give me the 10th bit of the proof, give me the 20th bit of the proof, give me the 30th bit of the proof. Okay. And we're going to measure how many parts of the proof you look at. Okay. So a probabilistically checkable proof, RQ, is allowed to flip R coin tosses and decide Q locations to query, and it'll get back, those bits. Okay. And okay. So okay, now the verifier is going to be given your input X. It can look at the whole input. And it's going to be given Oracle access to the proof, right? At some level, yeah, we're looking at these kind of sublinear checkers. And here's what we want to satisfy. Oh, okay, first it's going to make a certain number of queries after flipping some coin tosses. And then it's going to send the queries to the Oracle and get back the answer. So this model is going to be non-adaptive. You declare your queries ahead of time, and then you get the answer. That's slightly different than query, answer, query, answer, query, answer. Okay. And then it has to decide whether to accept or reject X. Okay. And what we want is that if X is in a language, then there should be some proof where it always accepts. Okay. And if X is not in a language, uh, then for all Y, it should accept X's probability at most 1/2. Okay. So we're looking at at kind of these probabilistic provers who are not necessarily looking at the whole proof. Okay, but if there's a flaw, if the answer is no, it should be able to say no sometimes. Okay, 1/2 is a little bit arbitrary. We can always somehow ramp that up, right, by things like repetition. Okay, uh, but yeah, so you should always accept if the answer is yes, yeah, and reject yes. Questions? So okay, so the verifier is a polynomial, is some kind of algorithm. So it's allowed to, so they as an algorithm, it can read all of X, and it's going to have some limited access to Y. I mean, at some level, it can access Y as much as it wants, but ideally, we want it to access it very little. It's more impressive if it can kind of access the proof less and still come up with some kind of conclusion. So verifier does refer to an algorithm. It kind of takes as input X and Y, but we're going to be careful about how it uses Y. Okay, and it's kind of parameterized by how many random bits is it using, and how many queries to the oracle to the proof it makes. Okay, so the proof is supplied. So this is again, uh, so yeah. So a language will be in PCP-RQ if there is a kind of probabilistic verifier of this type. Okay. Uh, so here's like at least an example that's really more of a joke. It's not a formal example, right? But if you TA'd undergraduate algorithms before, okay, and you're grading homework, if they solved the dynamic programming correct, it's like immediately easy to recognize they got it correct. And if they got it wrong, you know it's going to be a complete disaster, right? You can pick almost any random spot of their submission, and you'll quickly realize, okay, something's gone awry, right? So if you can come up with formalize this and come up with a good probabilistically checkable way, then you can, grade a lot of homework in sublinear time. Okay. But at some level, right, it is a question of sort of robustness, right? There should be some kind of like, uh, in other words, okay, so imagine someone's trying to convince you that X is in a language, but it's not. So they supply some kind of proof, right? But if this language has a good kind of PCP verifier, right? So they're trying to trick you, right? They're trying to give you a proof and try to convince you that there's a Hamiltonian path or something like this. We can specify the format. And this is claiming that, if Q is very small and R is very small, especially Q is very small in particular, okay, I should only have to check a few parts of the proof and still with, constant probability reject it. So in other words, no matter what they do, I have a reasonable chance of rejecting it. So at some level, it's like a very robust uh, verifier, right? The verifier sets up some kind of game where no matter what proof the adversary gives, you only have to pick a few spots, maybe selected at random, to realize that it's probably wrong. Yeah, question.
So if X isn't a language, then we're just saying that there exists something that has a probability we accept X is one. Or is there something?
No. So yeah, so there must be some Y that always accepts X, okay? And then if X is not in L, then for any Y, you can't get fooled more than half the time. Okay. So let me give you sort of a somewhat parameterized example. Suppose I'm trying to distinguish between like let's say I'm doing SAT or something, right? And I'm trying to distinguish between 1/2 minus epsilon satisfiable and 1/2 plus epsilon satisfiable. So I'm putting a little bit of margin in there. Okay. So that means, okay, your promise that the input is one of the two, or another way to put it is, if I gave you an input that's somewhere in between 1/2 and minus epsilon, 1/2 plus epsilon, either answer is okay. But if it's or it's kind of like saying 1/2. So basically, I want to make sure I reject with constant probability anything that's less than 1/2 minus epsilon satisfiable, and accept anything. Oh, this won't quite work. Okay, so this will not quite work, but at least it'll still be an interesting exercise. So this will not necessarily get probability 1 here. Okay, it'll be some probability less than 1. So it's not a perfect example, but at least it's something that's simple to maybe discuss. Okay, so suppose you want to sort of distinguish between 1/2 minus epsilon and 1/2 plus epsilon. That's sort of the game we're playing, and we want to do some kind of probabilistically checkable kind of prover. Okay, it won't quite be this as strong a guarantee, but what I want to make sure is that if X is at least 1/2 plus X satisfiable, there's some proof uh, where I only have to check a relatively modest number of bits in the proof, and with pretty good confidence say, yeah, it is 1/2 plus epsilon. And if it's less than 1/2 minus epsilon, then no matter the proof they give me, I will with pretty good confidence say it's less than 1/2 minus epsilon. That guarantee is slightly different than PCP, but it's still maybe a good point of discussion. All right, any ideas? Trying to distinguish probabilistically 1/2 plus epsilon and 1/2 minus epsilon.
You do the chart up and it just tries to squared.
Try epsilon squared what? Okay, we should specify a format of the proof. We get to specify the format, right? So what does the proof look like? Okay, so the proof is an assignment.
You check like epsilon squared as well.
Yeah, so we can randomly sample, randomly check. If you're just trying to get constant probability, roughly 1 over epsilon squared clauses. Okay, and that's enough to tell you with constant probability if it's at least 1/2 plus epsilon or less than 1/2 minus epsilon. Okay, so if you have a little bit of margin there, there's some robustness built in, right? If I'm just trying to distinguish between more than 1/2 by some margin, less than 1/2 by some margin, that actually gives me some room to sample, and I don't have to look at the whole assignment to conclude with some reasonable probability that it's one or the other. Okay, so yeah, but even that is not as strong as this because this needs to actually always accept something that's in the language, uh, and otherwise reject. I guess maybe what I could have done different is distinguish between 1/2 minus satisfiable and completely satisfiable, or distinguish between 1/2. I guess everything is 1/2 satisfiable, right? Okay, so maybe 9/10 satisfiable and 100% satisfiable. Okay, so yeah.
Just to clarify, when we say like if X is an element of L for some Y, like does the L depend on the Y? I kind of confused.
No, there's a fixed language. Like, does this the set of graphs that contain a Hamiltonian path? So if X is a graph that contains a Hamiltonian path, then there's some proof, which is the Hamiltonian path, written down in bits, that makes the verifier accept.
That's Y. Like the
Yeah, Y is the proof. But they just like to formalize it.
say X is L then L. Like L is defined to be a set of all graphs with an end.
Yeah. Yeah, that's the setup they like to do in complexity classes, often not so much in algorithms classes. Yeah.
We understand that the verifier and proof construction is equivalent to the description of a natural language. But there are like alternative proofs and ultimately verifiers.
So I think by verifier and proof, I mean, those are just kind of names given to ultimately an algorithm and a bit string, right? So the verifier is an algorithm. It's something written down. And Y is just a bit string. But functionally, it's acting like a proof. You can think of it as a proof.
I haven't seen it, but is it possible to show like non-existence of such verifiers?
Sure. So there are plenty of questions that aren't in NP.
What's the keyword you look for? Like showing.
So NP means that you can basically verify an answer when you find it. And you can verify it efficiently. But maybe there's questions where I ask a question and you propose an answer and I say prove it and we don't even know how to prove it. Yeah. It almost becomes, I mean, you could think of philosophical questions, but I think even questions like how many matchings are in this graph? Some huge number and there's no compact proof. Or, yeah, I think there's no compact proof, right? How would you prove to me that there's 1,004,003 matchings in this graph and that's the maximum? You can list all the matchings, but that's going to be huge, right? Because it could be exponential size. So that's not necessarily an NP, but it's a well-defined question. We have questions that aren't computable, right? That's what Turing proved. Yeah. And then we have religious questions and political questions and yeah, okay. All right. Good. All right, so that's PCP. Okay, this idea that this is a problem that not only has a verifier but has some kind of like very robust verifier. You can actually check and kind of decide one or the other, without even looking at the whole thing with pretty good confidence. It's something about robustness. Yeah.
Is PCP stronger than like an NP?
We'll get to the, yeah. So exactly. So the question is, how does this relate to NP? Oh, it also has something to do with R and Q. So one question is for how does NP relate to PCP then? Is either direction easier than the other?
One direction is
Okay.
because if we use 0 in this, like we use off the line, we can just use the NP verifier.
Okay, so you can think of NP as you don't need any randomness, okay, and you just need some to read the whole proof, which is a polynomial size. Okay, so that's maybe one definition of NP in this. There's no probabilistic left because there's 0 random bits. You can read the whole thing. Okay. All right. So here's then the dramatic result. So in other words, we can do something that's maybe more surprising than 0 comma poly n. A certain number of random bits, a certain number of queries. Anyone want to guess either? I guess queries is more fun to guess. How many queries do you think we need? In the worst case, overall, problems in NP. Yeah. Oh, let's do a vote. Okay. So who's not voting? Who's not voting? You can zoom in and write smaller. Okay, no one's not voting. Okay, so we got one polylog n. I'll put that up there. Any other candidates? Let's get the candidates first. Constant. Okay. Any other candidates? Just log. And then poly-n. Any others? Log. Fortunately, they're not written in order, but we'll vote in order. Any other? Poly log. Okay. Okay. So your choices are log, constant, log, polylog, log, polylog, poly. Let's say random. You need at least as many random bits as queries or something, right? So let's not worry about random bits. Yeah, let's say that each query needs log n random bits or something. Okay, so your goal is to pick the smallest number for which it will apply. All right, so we'll start with constant. Who votes constant? 1, 2, 3, 4, 5, 6, 7, 8. All right, 8 for constant. Now we have log. Okay, one person suggested log, and 0 people voted for it. Thanks. We'll never get those 10 seconds back. All right, how about polylog? Yeah, that's right. You've been shamed. How about log? Okay, this is popular. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14. How about polylog? 1, 2, 3, 4. 4. And then polynomial, in other words, the trivial bound. 1, 2. Okay. I mean, if it was polynomial, we just go home. Okay. All right. So log was the most popular, followed by constant, followed by polylog. Okay. So we have a nice bell curve. Well done, people. All right. Oh, amazing. 1, 2, 4, 8, 14. Yeah. Okay. So the PCB theorem says you can use log n random bits and a constant number of queries for any problem. Okay, so take any NP problem, and there's some way to format things and robustify or some kind of reductions. So ultimately, you only need a constant number of queries. Okay, and the log n random bits is really log n bits per query. It's just to pick an index. Yeah. Yeah, that's another way to put it. Yeah. So we already know 0 poly n, and you also get log n O1. Okay, so that might seem a bit, technical at this stage, but it leads to a lot of nice things. Uh, so from there, you start getting that 3 sat getting strictly better than 7/8 is NP hard. Okay, now there's quite a bit of legwork to get from the PCP theorem to here, and that requires a whole nother set of techniques that I've never actually even taught myself, and I don't know if anyone has. Right. But at some level, what is this saying? It's saying that figuring out if SAT is completely satisfiable or not is just as hard as 7/8 plus epsilon or not. Okay. So at some level, it's saying like up to 1/8 minus epsilon error, no error is as good as 1/8 minus epsilon error. There's no real distinction from a worst case point of view. Does that remind anyone of any other topics in this course? Some level, a moderate amount of error is about the same as no error. Yeah, it reminds me a little bit of error correcting codes. Yeah, you can think of this a little bit as saying I can take any SAT formula so that a single error will always get ramped up to like at least 1/8 error. Okay, but somehow, so somehow you want to take your 3 SAT error, which is almost completely satisfiable, but not quite. It's really hard to tell from a completely satisfiable formula. And then you still need to output a 3 SAT thing, right? So, and you don't want it to grow too big, right? Because it needs to stay roughly the same size. If you make something exponentially large, there's a lot of redundancy. It's not, so it kind of blows the whole polynomial verifier stuff. So you need to somehow make another 3 SAT formula. Maybe you kind of somehow layer in some redundancy. You can start to try to imagine taking a SAT formula that's sort of mysterious and trying to layer in redundancy so that at the end you get a 3 SAT formula that's still roughly the same size and is still 3 SAT. But if the original formula is satisfiable, this is still satisfiable. But if there was even the tiniest error or impossibility was the previous one, it's been ramped up to roughly 1/8 error, which is kind of the trivial what you get from 3 coin tosses. Okay, so in that sense, you can think of this as sort of a robustness kind of claim. Okay, and of course that has a huge, consequences because, first of all, we were very bummed out when Karp showed that, okay, a lot of problems might not be solved because they're equally hard. But then we responded with all these clever approximation algorithms. And there was a while where it was like, how far can approximation algorithms go? If we can get 99% of any problem, then who cares if we can't solve them exactly, right? Maybe it's like a very limited phenomenon. But this says, oh, there's also limits to approximations. Yeah.
Other limits of these.
Yeah, so we did set cover and we got log n approximation. That's also tight. You can't do better than log n. Okay. Yeah, there's lots of hardness and there's gaps and stuff, and it's a full-time job to prove hardness of approximation
Is that
votes.
the PCP?
Yeah, they all stem from PCP. Okay. So they're all statements saying unless p equals np, you can't do better than log n for set cover. Now there are sometimes also stronger things. For example, there's something called the unique games conjecture. Okay, which says you can't solve a certain problem called unique games, which is hard, it's not exactly 3 SAT, something a little more complicated. And there's various problems that we know is kind of unique games hard. So we didn't do max cut in this class. There's a famous kind of semi-definite program for max cut that's very elegant. Maybe if we have time, I'll sneak it in next week or something. But it's unique games conjecture hard to do better than this particular bound and stuff like this. So there's other kind of you can make stronger assumptions than p not equal to np and get stronger hardness results. Okay. All right. And when the unique games conjecture first comes out, people are like, well, yeah, but we don't know if it's true. But now it's been 15 years, so more and more it's like, it's been 15 years, 20 years, right? So, okay. And then you really open up there, and there's a whole zoo of conditional hardness and things like this. Yeah. For example, there's also a series of lower bounds, even for polynomial time problems like edit distance, based on the idea that you can't do better than basically brute force for solving SAT exactly. So solving SAT exactly, you need like 2 to the n, just to try all the variables. And we don't really have anything significantly better. You can improve 2 to like 1.9 or something. Okay. And if you can't really do better than 2 to some constant n, then you can't do better than n squared for edit distance. Yeah, so that's kind of cool, but it's kind of a different flavor. Okay, so much for hardness. Okay, all right. So here's another direction. I claim that PCP. So okay, we want to show that they're equal. But here's one direction, that PCP was log n random bits and a constant number of queries is an NP. Okay, so yeah. Okay. So why? So you can try. Okay, so if something is in PCP log n, okay, there's something that only needs log n random bits and checks a constant number of bits in a verifier. It'll always accept if the language is in, and it'll reject half the time, right? So that means you should be able to take X and the proof Y, and then you can just enumerate all the random bit strings. Yeah, and then just do every single possible and just run the verifier with all the bit strings. Okay, and then see if it came out more than half the time accepting or not. And then you can reject or accept. Okay, so if it's in, the verifier will always accept no matter the random bits in the queries for the right proof. And then if it's not in the language, then no matter the proof, half the time it'll reject. So you just have to try everything to figure out if it's half or not, or if any rejection or not. Yeah. Well, so the point is, to show that a language is in PCP, okay, we just have to design a verifier. So at some level, we can specify the structure of the proof. Like if it's SAT, I could say, well, give me the satisfying assignments. Just a n bit string, and I'm going to interpret the 5th bit as your assignment for variable 5. Okay. Now, since we're interested in this model, where we're kind of really interested in a sublinear number of queries. Okay. And of course, most algorithms, they take, normally on a computer, you give the argument as input, and everything already gets copied over to some extent. It's kind of implicitly reading the input. So to make this kind of distinction, we imagine like an oracle model where you don't get to see the proof unless you really ask for a particular bit. Okay, so the model is just it's some bit string, and then you just pick the location and it returns the bit. But at some level, when we design the verifier, we get to decide kind of what we expect the structure of the input to be. Okay. At some level, you're saying, I designed a system, and you can't fool me. No matter what proof you give me, if this thing is wrong, then I'm going to reject half the time while hardly looking at your proof. Okay. You can't convince me. You can't even convince a version of me that hardly looks at your answer, which is very useful for grading. Well, the verifier can use the R random bits however it wants. But I think here, I guess we'll, open up some of the proof, and we'll get a better sense of some of this is like, what form does this take? And maybe just getting into the proof will answer some of this. But you need log n random bits because each query is, log n bits, just to pick a random location. If you're doing a uniformly random sample, you probably want log n random bits for each one. Okay, good. And this is still like a, a pretty deep thing, right? This is my best interpretation of it. I'm not really in this field. I teach it because I feel like I should learn this better. But at some level, it's something that was proven, and we're still kind of letting it soak in. Okay. All right. Okay. So this direction is a little easier because you can enumerate all the random bit strings and just figure out which one it is. The other direction that we're going to spend a lot of time on is to show that any MP problem, you can create a PCP for it. All right, so all right, here's kind of one problem that we're going to start with. But it's any MP problem is basically okay. So something like three colorability is going to be convenient, as we'll see. But this is just I gave you a graph and I ask you if you can three color the vertices. That means you assign a color to every vertex, and every edge, the endpoints need to have different colors. Okay, it's one of our kind of favorite canonical MP hard problems. I don't know if I actually did it last semester, but anyway. Okay. Yeah. What can't make it into lecture sometimes makes a good exam problem. So three coloring is a nice example of so it's going to be helpful to do a slightly more general problem because we're going to kind of bend and reshape and transmove mess around with the problem, so it's not going to quite be graph coloring anymore once we start messing around with it. But it will be an example of a constraint satisfaction problem. So in constraint satisfaction, you just have variables and you have an alphabet. So each variable gets assigned some letter from the alphabet, or one of three colors. And then you have a bunch of constraints, right? Each constraint is over some of the variables and accepts some combination of letters or colors or whatever and rejects some others. Okay, so I think we're going to look at kind of like Q area satisfaction, like binary, trinary, whatever, if there's three variables in every constraint. And there's just simply, some combinations of letters that would get accepted and others that would get rejected. Yeah, so three coloring would be an example where each edge only accepts things when the endpoints are different colors. Three set is another example. Only, each clause becomes a constraint and it only accepts, true, false is the letters, and it only accepts if, x1 is true or x2 is false or whatever. Okay, so those are some examples, but in general, we're going to kind of start with something like graph coloring, and then we're going to do a bunch of like amplification stuff. So it won't exactly be graph coloring anymore, but it will still be a constraint satisfaction problem. Okay, so and what we're going to kind of do is okay. So remember, at some level, like take like the 7/8 hardness result, right? It's really saying it's very hard to distinguish between one total, kind of being able to satisfy all but one, or being able to satisfy all but 1/8 of them. Okay, so what we're going to kind of try to do is take, say, an input that can't be satisfied, and we want to kind of ramp up that minimum amount of unsatisfiability, so to speak, from like that one total to some constant fraction. Okay, so to that end, for some constraint satisfaction problem P, I'm going to let unsat P denote sort of what's the best you can do, minimum number of errors you can do. So 0 means it's completely satisfiable, and it's a min fraction. So 0.1 means at best you can get 90% of them right and 10% wrong. Yeah? And we want to kind of get that number up to a constant, 0.1, 0.2. I don't even know if we're going to get all the way up to the theorem, but it's not too important. Okay, so here's what we're going to directly try to prove in this kind of, actually, I think you can show this at least the PCP theorem. That'll be the next slide. Okay, the point is that there's some finite Q and finite alphabet size. It's not like some massive polynomial size thing, okay? That for Q area constraint satisfaction problems over this alphabet, alphabet size 5 or something, and okay, it's NP hard to decide if either it can be completely satisfied, so unsat is equal to 0, or if at most half can be satisfied, or unsat is greater than or equal to 1/2. So it's NP hard to distinguish between these two. Okay. All right, so hopefully I remember how to do this. We can do this together because normally this is an exercise in the homework, but we're kind of in that stage of class where we can't give out new homework. So it might be instructive to try to do this. It could be an exam. I think it might be a little long for an exam problem. Okay, so the claim is that this theorem in the original PCP, here I had this messed up last year, or anyway, this is mixed up. Okay, I claim these are equivalent. Okay, so on one hand, Suppose NP is equal to PCP with log n random bits and constant number of queries. Then why is CSP hard to get 1/2? So you have a verifier and yeah. So how do you take something that has a PCP and turn it into a constraint satisfaction problem where it's hard to distinguish between completely satisfiable or half the clauses or half these predicates or constraints can be satisfied?
Each clause is just one bit of the proof.
Each clause is just one bit of the proof. What does it mean to satisfy a bit? So it's not quite it, but yeah, we want to start doing something like that, right? Something needs to map to clauses. So how do I generate clauses? I think maybe that's a good way to focus on.
Again, random.
Okay, so maybe for each random bit string, I'll create a clause. Okay, and so what will be the variables for that clause? And what are the variables in general? So random bit string, what do you do, right? It has the verifier takes log n bits, 10 log n bits, and somehow it makes a constant number of queries, right? And then outputs yes or no. Yeah.
Salary checks if the random bit is the same as the first random bit in the proof. Check that. So it means that the random bit is the same.
Let's make sure we're on the same directions here. So you're assuming PCP first. So now you want to define a clause. So how do you define a clause? So let's go back to this. Okay, so for every random bit string, I'm going to create one clause. But what should be the variables for that clause? It's not all the variable because it's a Q array, right? So some subset of variables that really participate in this constraint.
The bits which are queried.
The bits that are queried. So the variables will be whatever kind of all the bits of the proof. So it'll be just the 0, 1 alphabet. Okay. And so every clause, every bit string, random bit string, I'll make a clause that's over whatever the queries would be for that random bit string. And the verifier somehow looks at these 5 bits and decides yes or no. And we'll just do exactly that for the constraint. So the constraint will be yes if the verifier answers yes for those 5 bits, and it'll be no if it'll answer no for those 1 bits. Okay, now how do we map the 1/2? Where does the 1/2 come from?
PCD accepts the term.
So the PCP, if the X is not in a language, it'll always reject with probability 1/2, right? So if X is not in a language, then you shouldn't be able to satisfy more than half the clauses. Okay, so that's where the 1/2 gets mapped in. Okay, so that's one direction. So basically, if you have a PCP, you can make a constraint satisfaction problem where every random bit string, which determines some queries, some particular locations, becomes a constraint over those particular locations. And you can only satisfy half of them if the thing's actually in the language. Okay, now suppose it's NP hard to distinguish between a half satisfiable or completely satisfiable constraint satisfaction problem. How can I show that PCP is basically NP hard? So basically, if I can come up with a PCP, then that will satisfy some NP hard problem, right? So satisfy all of them. So what would be a probabilistically checkable proof is, a few random bits, a few queries for CSP.
Let's look at some constraints.
Sorry?
Look at some constraints.
Okay, which constraints?
Random.
Okay, so if you looked at a random constraint, and then you just said, well, if the constraint passes, then I'll accept it. If the constraint's wrong, I'll reject it. Right? If the constraint satisfaction problem is completely satisfiable, there's some proof that satisfies everything, you always pass this random thing. And if at most half of it can be satisfied, then half the time you'll find a mistake and you can rejected. Okay, so just sampling one clause. Okay. All right. Yeah. So that's okay. All right. Good. So okay, so that's what we're going to try to prove. We're going to try to prove, you know, try to get this gap up to 1/2. Okay. Now, initially, you know, constraint satisfaction problems is of course NP hard because like graph coloring is one example of a constraint satisfaction problem, right? But in particular, in terms of kind of this unsat language, it's NP hard to distinguish between unsat p is equal to 0 or unsat p is at least what's the like bare minimum as a fraction. Yeah, like 1 over number of constraints. I wrote predicates, but constraints, like m if it was graph coloring, that's number of edges, right? So it's always NP hard to distinguish between 0 and 1 over poly n. That won't help you do a PCP because you'd have to sample a lot to find the one mistake, right? And now what we want to figure out how to do is somehow amplify your 1 over m, 1 over polynomial unsat up to 1/2. Okay, so you have some constraint satisfaction problem, okay? And you want to ramp up from, you know, polynomially small error to 1/2 error. Okay, any ideas? There's at least one natural idea that's guessable, yeah.
Like some checksums.
Try to make some checksums. Okay, that sounds nice. How?
Like something that's only satisfiable if all of the calls the same are satisfiable.
Yes, sure, but let's now get concrete. That's of course what we want too, right? So what's one way to do that? So you have some constraints, you can make new constraints. Let's say maybe you're allowed to blow up the Q array part a little bit and stuff like this. But in general, how can you ramp up and amplify the unsat? The end result should be like a checksum, but how? Yeah.
Constraints where it's like a new constraint that every like three subset your constraints are all satisfied.
You can start bundling them together, right? So let's say I pick 10 random, so I make a constraint like this. I pick a random 10 constraints at random, and I bundle them together. I say this big bundle's correct, satisfied only if all 10 underlying are correct, right? Now what happens to my error probability, roughly? By a factor of 10. Yeah, because you're choosing 10 and you're just trying to get the one mistake. So you have 10 chances to try to grab that mistake, as long as the mistake is very small. Okay, so that's a very nice idea. So suppose for every t constraints, I make a bundle of the t constraints together, kind of taking the and. You have to satisfy all of them together, right? That'll give me another constraint satisfaction problem where I'm just, you know, taking the intersection to make it kind of more brittle, right? Or that little error now shows up a lot, right? Because it's going to appear in a lot of bundles. So, okay. So what does the unsat p go like roughly as a function of t? Or actually precisely? So I'm going to do all the bundles of size t. Maybe allowing for repetition to keep it simpler. I think allowing for repetition. What happens to the unsat of the new problem? Sorry, it should be p to the t. Okay, what about roughly?
Here.
Yeah, it's going to go up by t. So more precisely, going to go up like 1 minus 1 minus unsat g to the t, or unsat p to the t. Okay. It should be a p. Okay. Now, how big does our problem become in terms of how many constraints do we end up with? Let's just fill out the rest. Okay. I just want to take note of how big our problem becomes. What is the alphabet size of the resulting problem? And what is kind of airiness? Is it binary, or assuming it was Q area to start, what area does it become? Okay, so how many constraints do we end up with? Yeah, I think I was doing this with repetition, so m to the t. 'Cause I think that made the previous calculation easier. Um, does the alphabet change? I think the alphabet does not change, so that's actually good. And then suppose it was like 10 area at first. There's 10 variables in every clause. Now how many variables are in every clause? Yeah, like 10 to the t, q to the t. Okay. So the good part is that we're ramping up the unsat and we're not messing up our alphabet size. And the bad part, uh, the bad part is the problem is blowing up too fast, right? So from like that error correcting code kind of perspective, it's cheating if I just add so much redundancy by just repeating or something, right? What you're really interested in is sort of the overhead of adding this redundancy. So right now our overhead is too big. We're blowing up the QT array. The problem size is getting big. For example, if we start at 1 over m, what do I need to make t until I start making, get up to a constant? Yeah, you got to do t equals m or so, right? Something on the order of m to get this thing up to a constant. And suddenly you're looking at m to the m size problem, m to the t or q to the m array problem, right? So it's so big that, saying that once you're up, blew it up to exponential size, and this whole like, what are you doing in polynomial time? It's not a reduction anymore because you're already spending exponential time building the thing. It's not polynomial time reduction anymore. Yeah. Okay. Okay. So those are the main issues. It's just that we do want to amplify like taking a product, but just directly kind of bundling things together is bad. Okay. Does anyone want to try to guess a way out? I don't know if this is guessable, but at least it's your only chance before I tell you the answer. So it's fun.
The expander.
Okay, expander is a good word. So let's interpret that. Why?
It's the other thing that you did, like depowered it.
Uh, is there a more kind of context independent explanation?
Like you can simulate their randomness.
Okay, so we can try to simulate randomness with an expander. Okay, how can we start imagining? So this is a constraint satisfaction problem. So how can I sort of imagine it as a graph? Like what should the nodes be in if we're kind of working with this expander analogy? What should the edges be?
And those are the variables.
Maybe nodes are variables, edges represent, sorry?
Like, pluses that way.
Yeah. Okay, maybe like a hypergraph. So what would be an edge in a hypergraph?
Would be a constraint.
Okay, so it could be a constraint over all the variables. Okay. And in particular, if you had a binary CSP, only 2 variables per clause, like graph coloring, that would be a graph like you're used to. Okay. Now, okay, so let's say that you did do like a graphical CSP. So it's going to be binary, and we can think of all the variables as vertices. And for every constraint, I'll think of that as an edge between the 2 variables. There can be parallel edges for multiple constraints over the same vertices. And okay, so that's fine. Now, okay, now you could still do this where you just bundle things willy-nilly, right? But then you're gonna exact same problem because you're doing the same thing. It's just Q gets replaced by 2. But what could you do different in a graph that might also work really well for an expander? An alternative to sort of this complete bundling. Powering. So what does powering refer to? What do the constraints look like?
Like you want T edges and only pick those T.
So I can imagine T-step walks and then taking the bundle of those constraints. Okay, so instead of taking T uniformly random constraints and combining them, if all the constraints could be visualized as a graph, like a binary CSP, then you could start doing stuff like here's a 5-step walk, and I'm going to kind of combine that into a single constraint, right? And that's going to at least let me ramp up the unset G. Okay. And then one thing nice, suppose it's a constant degree graph, like a degrees 5 or something. How many constraints would I generate? Yeah, you're going to be generating d to the t times n or d to the t times m or something. Okay. So, it's exponential in t, but at least it's not, there's no bm in the polynomial. Right? So for up to t equals log n, this is actually kind of okay. Now, what are some issues with this analogy? What? Well, it might be binary to start, but once I look at this and I kind of combine this, now I have 5 variables if I was taking a 4-step walk, in the underlying walk, right? Which, I could still replace as with an edge between the endpoints, but now it gets confusing because somehow this variable, this vertex and this vertex in your power graph needs to somehow represent these variables. Does that make sense? So if I want to think of every 5-step or 4-step walk as a constraint, I can either think of that as like, well, now I have sort of this humongo edge with 4 vertices inside, a hyper edge, right? Or I can think of that as like in the power graph, that would be just one edge between the endpoints, in g to the 4 or whatever, right? But somehow the endpoints, there should be 4 variables involved in these constraints or 5 variables involved in these constraints. And somehow you only have 2 vertices, so that also gets screwed up. Okay. So that is the direction we're going to go, but those are some of the issues we'll have to think about. But the key intuition that you guys have kind of honed in on is that if this is an expander, I don't have to generate nearly as many constraints. And because of the kind of mixing type of analysis, I'm hoping that I'll still get the effect, okay, of completely uniformly random bundling. Okay, good. So I think we're setting this up well. So yeah, so we're going to look at graph CSPs. Again, 3 coloring is sort of our starting example. But this is basically the same as binary CSP because any binary CSP you can imagine as a graph. Okay, by making every variable a vertex. Okay. So okay, and we know it's NP hard just from 3 coloring to distinguish between unsat 0 and unsat 1 over m. Okay. And the question, as usual, is how to amplify this up to a constant. And again, we've already done the idea stage, but we're going to try to somehow make this thing into an expander and stuff like that. So this is going to start looking a little bit like what we did for the deterministic connectivity, where we sort of take some kind of graphical constraint satisfaction problem, and we're going to try to massage it. Our real goal is to ramp up the unsat from 1 over m to a constant. I don't know if we'll get all the way to 1/2. We're just going to try to get to a constant. We'll call it a day or a week. I think you guys will be exhausted by the end of this and you won't care. But just naively powering is going to cost some stuff, and so we also have to do some cleaning up and fixing. Okay, so first of all, that powering only worked if the graph was what, or only worked well if the graph was a constant degree expander. So step 1 is we're going to have to take our constraint satisfaction problem and turn it into a constant degree expander. Okay, and that's just prepping for some kind of powering step. And I'll explain what we actually do to resolve this issue of kind of, if I take a walk, there's only many variables seemingly implicit in what's supposed to be an edge between 2 vertices. Okay, but a net effect is actually going to blow up the size of the alphabet. That's how we're going to resolve that thing. And it'll make sense when we get there. And so the last step you have to do is reduce the size of the alphabet. And this is where we're going to black box some things. Okay, but hopefully by step 3, you're exhausted. Okay. Okay, so those are the 3 main steps, but you're gonna just go around in a circle. So you're gonna make it well connected with an expanderification, so to speak. And that, each of that might give back a little bit on the unsat. Yeah, you make some adjustments, you lose a little bit on the unsat. And then you're hoping to gain a lot in this powering step. But the alphabet size is gonna blow up, And then you're gonna have to reduce the alphabet back down to a constant. And then repeat, repeat, repeat. And somehow you're gonna make progress in each cycle. Okay, it's gonna be sort of like we did with deterministic connectivities. We're just gonna have to multiply everything together and see that indeed you did have a net win all the way through. Okay, good. So I think we can at least do the first one before time's out, and maybe introduce the second one so that you can let us soak in overnight. All right, so we're just gonna we want to make a constant degree expander. We're just gonna take this into 2 steps. Step 1, make a constant degree. Step 2, make an expander. And this is actually guessable. Yeah. Huh?
We're using G now.
Yes, I'm referring to the problem as G because it's like a graph CSP, and we're really kind of focusing on the graph. There's always, all the edges are annotated by some CSP logic, but we're really kind of focusing on the graph structure. Okay, so, all right, step 1, we want to make G a constant degree graph. Don't worry about the expanderification stuff, the expanderness, just constant degree. So here's like a high degree vertex, has lots of edges. How can I make a constant degree? Okay, we can split, and I thought of a really cool way to demonstrate this. Okay, so we can split it like this. I can like pull one off here, pull one off here. Yeah, I can start splitting these up into multiple vertices, right? This is what you had in mind? Okay. You guys only seem mildly impressed by what is sort of the peak of my teaching abilities. Okay, so now I'm splitting these things up like this, and then what? Okay, how should I add edges in between? Like a tree? Yeah, just pick any, but well, a tree might require introducing new nodes. What's an easy way? Maybe a cycle? Okay. Now, we have to add constraints to those edges. So what should those constraints be? They're all equal. So whatever letter you assign to kind of your split, maybe you make this different color. Whatever letter you assign, right? You want them to be equal, right? You shouldn't be allowed to like say, for this constraints I'll choose this letter, and for those constraints I'll choose those letters. Okay, that's very close to the ultimate thing, but there is a flaw. Now I want to point out, if you're doing exact CSP, then those constraints will be just fine. You have to satisfy all the constraints, so they all have to be equal. But we're not quite doing that here, right? We're interested in, margins of error, how much you're getting wrong, right? So for example, if I find it convenient to have these one set of letters and that another letter, I only have to make 2 mistakes, and possibly I get a bunch more correct than I would have been able to, right? So I want to do something like this. I want to split the vertex. I want to add a few edges, but I want to make it robust. So like here, I shouldn't be able to split it in half, right? And give the 2 halves different colors, okay, or different letters. Well, basically only cutting 2 of our constraints, right? Cutting a very small number of constraints. Yeah.
This because then with the subset you have lots of edges.
Okay. So this is like a low conductance cut, right? You're cheating on a lot, but you're only making a few of the auxiliary mistakes. So if I had more robust connections, then that would be great. Now I want it to be constant degree. So I can't just connect everyone. If I did a fully connected graph, that would of course resolve my problems. Then I would never want to mess anything up. But if I just added a constant degree expander, then there should be a fair number of edges across any particular cut. And that'll be enough to dissuade you from cheating. So we are going to split the vertices. I feel like there's way more text here than necessary. We are going to split the vertices, But instead of adding something totally simple like a cycle, we're going to add some constant degree expander, something that's a little bit more well connected. That's supposed to be an expander. I mean, I just made it up. I have no idea. But something that's still sparse, so the whole thing comes out small degree, but has a fair amount of connections in between. Okay, so if you do start cheating, you're going to introduce a lot of errors, kind of on the crosscuts. Okay, so
It's not that error, like that error that you get that you save from.
yeah, so now, okay, so here's the claim, right? If you do this. So what do we care about? One is that the number of edges don't go up too much. That just comes from splitting each vertex and adding a constant degree expander, right? So all of the internal edges can be charged off to the outside, right? There's constant degree, and every vertex represents one edge in the original graph. So you size of number of edges didn't go up too much. The second claim is that it's regular. That's again fine. Okay, that's also not that interesting. And then the more interesting one, this is not going to be very satisfying to Wilbur, is that the unsat only goes down by constant factor. So I can take anything that's satisfies a bunch here and plug it into G prime, in which case it's going to get all of the edges inside the expander correct for free. Okay. And it's going to get the same ones right or wrong on the original problem. So unsat's only going to go down, but it's not going to go down by too much. Okay. And I guess in the opposite direction, as long as you add enough edges in your expander, then a single mistake or 10 mistakes, if the conductance is at least 1, then 10 mistakes on one side, you're guaranteed at least 10 edges across the cut. Okay. And if your first expander is not high enough conductance, just repeat it, right? Make as many copies as you need until the conductance is at least 1 or something, so that whenever you have 5, or that the sparsity is at most 1. So whenever you have 5 vertices on one side, is the smaller side, there's at least 5 edges across the cut. Okay? Because these 3 vertices are only satisfying 3 of the original edges. So as long as I guarantee that this picture is okay. Okay, so if I pick these 3 vertices and they had different letters than everyone else, then I'm still going to make at least 3 mistakes across the cut. Okay, so I want to add enough connections across the middle. As long as it's a constant, it's fine. Okay, it might, that constant might be 10 or something, right? Maybe the number of edges goes up by a factor of 100 and unsat goes down by a factor of 100, but that's going to be okay. Okay. All right, good. So that's it. That again is, if we had time to do homework, I would assign it. Yeah. Yeah.
It's not gonna be like exactly because we made the example. There's like a 30 edge.
Oh yeah. So I mean, I made the example, so don't worry too much about the example being flawed. So in general, you're going to add a regular expander where that's already regular, and to split. In fact, I didn't even split as aggressively as I could have. We could have split it so that instead of doing 2 at a time, it would have been 1 at a time. Okay, so that means every vertex in here is going to have exactly 1 vertex originally, and then whatever its constant degree from the expander. So as long as the expander I use is regular, then the resulting graph will be regular. So that's not too bad. Okay.
Wait, are we proving this?
No, this is an exercise. Well, by exercise, I mean you could do it. It's kind of straightforward. You just have to verify it. There's no massive ideas. Okay, it'll just confirm the intuition that we just went through. Okay. It may still be good for you to do, just to make sure you're comfortable with the definitions, though. Okay, so we should at least be able to do step 2, and then maybe I'll introduce the next thing slide, just high level, and then we'll call it a day. So next one we want to do is make the graph an expander. Any ideas? This is again guessable, right? Maybe G looks like that. It's regular, but it has bad expansion. Uh, hmm?
Powering.
uh, well, powering is going to mess up the degree and stuff, right? So I don't want to mess up the degree. I should maybe mention one thing. Before we had to be really careful, like with connectivity, because we weren't allowed to introduce new connections and stuff when we were doing SD connectivity, right? So we were constrained to doing things like powering and stuff that kind of maintain the integrity of the underlying input. But here you don't have to, right? It's constraint satisfaction. You can do whatever you want. You're worried about unsat, getting corrupted a little, but okay, add some edges at random. If I didn't want to do it randomly, so this is actually kind of simple. We're just going to overlay an expander. So just take any expander with the same number of vertices as your graph, okay? And just throw it on top, okay? With like, constraints that are automatically satisfied or something, okay? So it does nothing as far as the constraint satisfaction really does. It's just dummy constraints, but it makes your graph kind of well connected. So you just throw an expander on top with dummy constraints, okay? And yeah, your unsat went down a little bit. It didn't go down too much because it's expander, so you didn't add too many constraints, you know. So number of edges maybe only went up by a factor of 10, so unsat went down by a factor of 10. Okay, you're going to get some big boost later, so that's okay.
How big is this boost?
How big is the boost? We'll find out on Thursday. Okay, but that's how you make an expander. In fact, it's very simple. That's not the hard part of the proof. You split it with an expander and you overlay an expander. And you lose a little bit. Okay, so powering. All I want to do is explain what the operation is, and that'll brace us for the real effort next time. That's going to be most of our work because the last part we're going to black box a little. Okay, so again, we're going to take those random walks. Okay, so like before, so we're going to have a constraint for every t edge walk. Okay, the only question is how do I turn it into like a binary CSP with two vertices? Okay, so what we're going to do is going to blow up the alphabet size. So for every vertex, let's say I'm taking 3 edge hops, right? So there's some 3-hop neighborhood of the graph, okay? And at some level, what I'm going to do is I'm going to think of assigning a color to this as actually really assigning a color to all of its neighbors. So what does that mean? So the alphabet size, so let's say D is the total number of vertices. If you work that out, it'll be 1 plus a degree to the T, okay? Or that's an upper bound anyway. Okay. And what you're going to do is you're going to assign enough colors to V or enough letters to V so that each one can be interpreted as a letter for a different vertex around here, right? So at some level, this is going to kind of have an opinion for the whole neighborhood. This will contain all the constraints that it participates in. Okay. So at some level, each vertex is now going to have a ton of letters, which can be interpreted as, labeling its entire neighborhood. That'll swallow up all the constraints. And now when I make a constraint, right? So I have some constraint, from V0 to VT. What I'm going to do is I'm going to look at V0, which have a bunch of letters, one for every vertex along the walk. VT also has a letter for every vertex along the walk. Now, what's the sensible way to decide if this kind of long walk is satisfied? This is guessable, although I don't know which is A, B, and C. Every edge is satisfied by. So for example, V0 has letters for each one. So V0 should satisfy every edge. Yeah, that makes sense. And VT also has letters for every single one. The underlying graph is undirected, so it does go in both directions. Okay. So VT also should satisfy its labels for the neighbors, should satisfy every single one. And there's one more thing that's like a reasonable check. They should be the same. They should agree on the labels for everyone in between. So that will be our 3 requirements that both of the endpoints, they're kind of multi-labeling, will satisfy all the individual things on the constraint. And not only that, but they're agreeing, so they're not cheating, right? This way, if you had originally a satisfying formula or a satisfying assignment, you could use those here and there, and it will satisfy all these things. Whereas otherwise, you're likely going to break and cheat something. Okay? Pi is a labeling. Yeah, so that's a little quick, but then we'll warm up again revisiting this. But that's the operation that we really want to analyze this next time. Okay, yeah.
So we not have intermediate. We want to V2 minus 1.
Yeah, we'll ignore their color. Yeah, they have individual colorings and stuff. Because at some level in my power graph, I want to just be able to look here and see if this is satisfied. Because we want a binary CSP afterwards, right? That's why I'm only looking at V0 and VT. Okay, all right. All that next time. Thank you.